Greetings and welcome to this third video in this series where we started out learning about stress, both normal and shear. And in the second part, we reviewed what yield strength is as part of a material. And in this third part, we will be considering design factors for material stress. And it might also be referred to as why mechanical systems must be designed for more than a load and a yield strength, based on our previous two videos. Or another way of looking at it is why good enough usually isn't. So why do we have to design and consider more than just the load and the yield strength? First off is the loading type. A static or dead load, such as these lights, is a very simple and fairly easy type of loading to design for, but many loading types are not this simple. A live load, which is cyclic or variable. So if you see this robot moves and picks up boxes and so on, and it does it over and over again. In fact, most failures come as a result of repeated loads, whether they are cyclic or variable. Cyclic would be the same load over and over again, whereas variable, the load itself might change, the frequency might change, so on. Another type of loading would be sudden, whether it's shock or impact. For example, this is the patent for a pneumatic hammer, or a jackhammer as is often referred to. So the design of this jackhammer have to consider the fact that many of these parts will be under shock or impact loading. And that's going to be very different than a live load or a simple static load. The mechanical properties of the materials that are used are very important to the design factors that we consider. For example, ductility, like this is stretching, versus brittleness. This particular material, notice how it didn't stretch, it barely deformed at all, it just broke in a very brittle fashion. That's a very important consideration. Strength, well, what kind of strength? As we already considered, there's yield strength, but there's also ultimate strength. This vehicle did not do well in this particular encounter, and so therefore its ultimate strength of many of its materials was exceeded. Resilience. Springs are a classic example of resilience, so you could use them over and over again as they store that energy that allows them to snap back. Toughness is a material's ability to withstand and absorb energy. Hardness is its ability to withstand indentation, and there are many others that are very important when one is considering the design of a mechanical system. The environment that it is used in is very important as well. Is it indoor? Is it outdoor? Indoor might have some forms of dust. Outdoor might have the elements. This is an implant right here. There are many issues with where this is implanted and how it can affect and be affected by the structures and an environment around it. And there are other types of environments that are important to consider. What kind of temperatures are these mechanical systems undergoing? So here we have a gas turbine, and it starts out supposedly room temperature, but as it heats up, the mechanical system still has to work properly. Maybe it's in flight, and these materials on the outside are actually quite cold, being at 30,000 feet, and the inner parts are at much higher temperatures, so it has to work in all of those situations. The turbine here also vibrates a lot, as if you've ever ridden on an aircraft, there's a lot of vibration all throughout the aircraft. they try to minimize, but it's still part of what needs to be considered in the environment. Last but certainly not least, other safety factors and standards are in play. What are maybe some additional risks to life and limb? This crane has many parts that are very important for the safety of these workers. And on top of that, if this load were to fall, the load could be damaged, the turret here could be damaged. So there's risks to property as well. Simply liability, need to make sure that we take proper precautions just because of the legal environment. There are many unknowns in certain situations. You just don't know. What is the wind on a day like this? Is that going to cause a problem? Not quite sure. So we have to consider that there are some things that just might show up as a risk. So need to consider those as part of safety factors. Finally, and most importantly, actually, I saved the best for last here, are the codes and standards. So for this cable, perhaps for this hydraulic cylinder, for welds, for pressure vessels, there are codes out there by the American Society of Mechanical Engineers and many others, the American Society of Civil Engineers, American Institute of Steel Construction. All these different societies have codes and standards for certain commonly used materials that have these types of risks. So that would actually be one of the first places one would want to go to determine what types of materials and how they should be designed with what types of design factors. Now, you've heard me say design factor. There's also something called the factor of safety. Often these terms are used interchangeably. I try to separate them into two different types of things. I like to use design factors when I am designing. So if something seems to be in a certain environment that requires a design factor of 1.5, then I include that as I'm designing. But as I'm designing, other things may change. So that's where the factor of safety comes in. So the design factor I use to specify and develop a design, and is determined by all the known factors. So maybe one's 1.5 and one's 1.2 and one's 2.0. So you multiply those together. Perhaps that might be one of the ways in which that is done. Then you end up with a design factor, and you design from there. So that design factor, it may not be the same factor for each part. There might be some more known factors, or it might be a weld, so it would be a different failure mode. So you're going to have a design factor for different parts or failure modes, and depending on what is known for each. So the factor of safety is what results. It's calculated after each part or failure mode after the design iteration is set. So this is what happens after. What is your factor of safety? And it can be looked at different ways. So if you're going to use this method, design factor, then factor of safety, it needs to be spelled out exactly what you mean by factor of safety. You take the factor of safety and you review it once you've calculated it against your knowns and unknowns. Had situations where a complex design, there were some unknowns as to how the stress was actually being distributed, so I had to have a higher factor of safety because it was not quite sure how it was going to operate. There were other parts of it that were much better known, much clearer as to what was happening. So that was more comfortable with a lower factor of safety once all the design factors had been considered. There's another thing called the margin of safety. That's a slightly different calculation, but it's also an appropriate way of considering these design factors and factors of safety. And it's always best to refer to those standards from the different societies to determine the appropriate factor of safety. It's hard to go wrong with that. Okay, how to apply the design factors. Well, first off, if you're using codes or whatever, you should review your tables. So we're going to continue on with our example. Next, we return now to the example we had of the clevis, the pin, and the tang, where we had the tang with the load here, the clevis here, and the load being transferred through this cross-section and through the pin at these locations, causing shear stress, and this would be normal stress. So remember, we've got both shear and normal going on here. Now, when it comes to the design factors for these, if you look in the book that we use, you'll see that for static loading, and that's just what we'll do this time around. For static loading, it has a recommended design stress of the yield strength over 2. So what does that mean? That means that we are trying to keep under this value for stress for our design. So that value is 1/2 of the yield strength. Remember, the yield strength is up here, so we want to keep under half of that. So that means we're trying to stay in this range here for our design. So that is for our static load, but that's also in normal stress, because that makes a difference as well. So we can calculate that out for our normal stress here as 250 megapascals divided by 2 is 125 megapascals. So in order to compare it, we want our design stress greater than the applied stress. But as we found out up here, our applied stress is 150 megapascals. And guess what? That means it's not good. So what do we do with that? Well, you might say, well, why don't we just wait on that? We already know what our area is, and we already know what our loading is. Why didn't we just calculate that right off the bat, figure out our design factors, and then choose our material? Well, turns out that that's what we should have done in the first place. You're right. So let's do that. We know that now we need a material that has a design stress of at least 150 megapascals. That's what we want. We want something with a design stress of at least 150 megapascals, and that means we need a yield strength of twice that. So let's rearrange our equation there. The yield strength of our material has to be greater than 2 times our applied stress. And our applied stress is 150 megapascals. That means that our yield strength should be greater than 300 megapascals. Now, I'm going to look at this chart, but this is a very small selection of materials. So I think I'll just go straight to a steel chart. And this is a chart from a steel manufacturer, and they have the yield strength here in megapascals. So I'm going to pick something from here. So what we're looking for is something that is at least 300 megapascals. So this A36 structural hot rolled, that's as we found out, not good enough. But we could use the cold drawn steel alloy, but this may not be workable. I think the 1020 normalized that has 345 megapascals of yield strength will work just fine for us. So let's go back here. At the very end, I will say specify 1020 normalized, where the yield strength equals 345 megapascals. Now this is where that difference comes in between design factor, which we found was 2, and safety factor. Now that I specified something that actually has more strength than what we need, now I can find my factor of safety based on yield strength is going to be the yield strength divided by the applied stress, 345 megapascals, divided by the applied stress was 150 megapascals. And that gives me a factor of safety of 2.3. And that's in the normal stress for that particular part, which is the clevis. Okay, let's look at the shear. Okay, so for shear stress, our book says our design shear stress is to be 1/2 of the design normal stress. So that's, as we see here, half of the yield strength. So this makes it 0.5 yield strength over 2, or to simplify it a little bit, the yield strength divided by 4. Now we used a different material on the pin, and their yield strength there was 703 megapascals. And we take that, divide by 4, and we get 176 megapascals. So this is our design stress. This is sometimes referred to as allowable stress. We do not want to go over this stress. But guess what? Our applied stress is back up here at 191 megapascals. So we want this to be greater than our applied stress, which is 191 megapascals, and it is not. Not good. So that didn't work out, and that didn't work out. So what we need to do is change the material again. We're going to redesign it. So again, the same way we probably should have just done this right off the bat, is not worried about which material it is until the end. So we want the yield strength of our material to be greater than 4 times the applied shear stress, and that makes it 4 times 191 megapascals, and that would be 764 megapascals. So let's see if we can go back and find a material that's going to work. So we need something that's more than 764. Well, most of these are in the middle hundreds range. Now here we have a 4140 oil quenched and tempered at 1570. That might be a little bit too much there. But we could go with that, or we could go with the 4340 normalized. So why don't we do that? 862 here, and specify 4340 normalized, yield strength of 862 megapascals. So now we can calculate our factor of safety for that. So our shear strength, which is going to be Sy over 2 divided by our applied shear stress, is going to be 862 megapascals over 2 divided by 191 megapascals, and that calculation gives us 2.26. So our factor of safety in shear is 2.3, and our factor of safety in normal is 2.3. Doesn't usually come out that way. Usually one's larger than the other, and your actual factor of safety is the smaller one. So this is for shear stress on the pin. Now, another thing that has to be noted is that these are very general rules that we found in the back of the textbook. This is more of how to apply design factors than necessarily the right factors that are for use in a real situation. But hopefully this gives you a good idea of how they should be used. Now, another very important thing to do is review your work. If it looks like you have a material that is weaker than your applied load, you need to say, where did I go wrong? Look at the different values of the different things and see if they make sense. Use some critical thinking skills, because it's very easy to misplace a factor of 2 or multiply by the wrong number in your calculations. So it's very important to go back and see what makes sense. We started out with calculating simply the loads, which are 150 megapascals of stress in normal and 191 megapascals of stress in shear. But after reviewing what yield strength is and how we're basing our factors on yield strength, we ended up with an okay result for normal stress using the A36 steel for the clevis, but a not okay result for using A36 steel for the pin. So we had to change that to the tool steel. Then when we considered other design factors, often simply throwing a factor of 2 in there just because there are many unknowns and so on, reviewing what the design factors are based on, we had to change the material for the normal stress so that it had a higher yield strength. We started off at 250 with the A36 and we changed to the 1020 normalized, and we ended up with a higher yield strength because of the added design factor. And the same thing happened with the yield strength in shear. We ended up changing the material again because of the added design factor. Finally, we calculated the factor of safety for both of them, making sure that we had over a 2 factor of safety because our design factor itself was 2. We wanted to have at least that. Well, I hope this series of videos has helped you understand the differences between normal and shear stresses, what the consideration of yield strength is, and why we have design factors and how to apply them. These are very important and basic elements of strength of materials or mechanics of materials. I hope you continue to tune in to my other videos to help you learn even more about these important topics. Thank you.